Hello reviewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about India's step towards nuclear sovereignty. So let's dive deep into it. So what exactly is the problem? Well, India declared itself nuclear armed, meaning we can boom anybody, in 1998. Now the first boom event we had was from Smiling Buddha in 1974, this one. So we started, we gained competency, and we reached till hydrogen bomb. So we got this. However, how the heck we got the material? Well, we didn't, we bought it. So civilian grade uranium. Now India does have some uranium, but A, it's distributed so much, and B, the concentration and quality as in the enriched material part, that's not that good to be useful. We have it. We do have some mining, enterprise on it, but it's not that useful. So we get civilian grade uranium. Over time, we cook it into civilian reactors, which become plutonium. Plutonium becomes the boom element. And India has a very good competency on nuclear. And I mean, not only in terms of kaboom, but in also terms of power plant, which is ironic. Like India has surprisingly bad tech tree when it comes to electronics. And I mean, from base component level, we're good with nuclear. Like everything about nuclear, we're like, bro, we got this, we good. But we lack the raw material supply chain. We have everything we needed for basically silicon technology, but we don't have competency. We have all the competency needed for nuclear system. We don't have the raw material. So irony. And we have endless supply of thorium reserve. And let me be very clear, it's not that India have decent amount of it. World's largest reserve. Like there is no discussion. That's how much thorium we have. And be mindful, given the fact that USA is 3x larger in surface area, we still have more, including China. China is very small thorium reserve. So, and again, most other countries had luck with uranium, so they did not develop that thorium technology as much. We have a unique scenario where we have almost zero uranium, but boatload of thorium. So we are stuck in this weird loop. We know how to build these things, but we have no fuel for it. So what can we do to use thorium directly? That's the key aspect. We have to let go uranium and we have to go to thorium directly as a feedstock, meaning you put thorium in the reactor gives you electricity. That's what we want, not this. And by the way, we don't buy uranium, we buy uranium ore. Then we refine it and process it. So Homi Bhabha, he's a very genius man, and he came up with a 3-stage plan. Now, sometimes I do have to say, there are a lot of elders in early India that laid down a foundation that was like, God damn, that was good. Like they thought out so far ahead that it was like, really, man. Like you saw future before future became a future. It was like, damn. This was one of that. So it's a very long term, like, remove the delay that happened, but day one it was designed for 30-40 year plan. So it was like, it's gonna take a sweet time and we're gonna push through it. So that was the whole point. And idea was, we're gonna make our own fuel, meaning we'll be completely self-sufficient. We will not have to ask Canada or Russia or France or other nations for material. We're like, we good, bro, we good. That's what we want. Now, imported natural uranium ore that we get right now. Now, let the be clear, nobody has shared, or I could not found a source for it. So I do not know what is the concentration of U-235, the boom part, into the normal uranium. So let's just go with 1%. So what do you do with this? Well, we had good partnership with Soviet Union. So we learned something known as pressurized heavy water reactors. Now, pressurized heavy water reactor has the one unique advantage. It does not care about the fuel purity. Like it's like, bro, we good. It can work with surprisingly, almost natural material it can digest. That's how good it is when it comes to like, just taking uranium and crunching it. So we cook in that reactor and that gives us few output. First is depleted uranium 238. That is the natural one. That was not reacted with any single, that's the normal. But here's the deal, you have so much of it and 235 was reacting that neutron was created. Some 238 get married, forcefully married with 238 uranium. That gives us plutonium 239. 238, you force one neutron into it, 239. Ta-da, plutonium, the boom material. So we get plutonium. However, if we can do that, if we can do the transmutation directly, why not just transmutate thorium into something useful? Well, neutron economy is weak. This reactor, really good for what it is. Not that great if you want to directly digest thorium. So weak neutron economy equals we cannot convert thorium into U-233. We can't. We can't do that. We can't get 235. We can't get 23. Like we have 238, but 233 won't be there. And again, we can't just, here's some thorium, convert it, please. It will not work. So that's how it works. Now, stage 2. So that was the first normal reactors that we have right now. That's a normal thing. So you take uranium-235 reactors, you feed in raw uranium ore, you get power and electricity, and then you get basically depleted uranium, plutonium, and then you feed thorium-232 into the next stage. Second stage, which became active right now. Second stage is a what we call breeder reactor. Now, fast neutron, that's the key aspect. It needed rich economy of neutron. How do you make a rich economy? Remove water from it. Water is a very good moderator. So you're like, no water. What is the other options you have? To be clear, some people do claim there are certain topology that should allow you to have fast neutron with water. I have not seen them. But this whole idea is replace the water action with sodium. Sodium is almost purely transparent to neutron, meaning neutron released, it just goes yoink. Like it does not slow down. It never goes from fast neutron to thermal neutron. It just yoinks. So that's how we went into sodium reactor. Sodium is the coolant. So we feed 3 puppies, which is 238 depleted uranium, 239 output of first reactor, 232 we got more than enough, and then gives us 233. Why? Because transmutation happens. So why we have neutron? Why? Because fast neutron is freely moving around. And that's the feedstock for the third stage. Now, third stage is the key. This is what India wants. That's why we are working our ass off. So third stage is U233. Once we have enough U233 to ignite that reactor, we will have the luxury of basically cooking thorium-232, basically raw thorium that we have right now. So you take thorium TH232 and force a neutron in a forceful marriage, and voila, it gives you U233 as a fuel. Basically, this reactor, once you ignite it, once it's like, okay, it's running in a fission reactor because you fed 233, it does require starting amount of it, whatever it may be based on the design. Let's say you put 1 kilo of it just to get things rolling. After that, you can keep just the rods, you keep inserting thorium into it. Thorium over time will convert into 233. You don't have to worry about it. And yes, it does come with one design workaround, that your reactor must be actively maintainable, meaning there are reactors that you make it, seal it, don't touch it for 10 years. This is not like that. This reactor would be like, you seal it, but you should be able to replace fuel rod, because again, we'll have like, okay, we put 1 rod, next week we had different rod, and we keep doing it for 52 times, and then, okay, the first rod we put 1 year ago, now pull it out, now it has all the material transmuted. So thorium and neutron gives you that system. And again, it's a very long chain. Basically, thorium first becomes 233 with 143 neutron. Then it has a negative beta decay. Then it slowly comes down to what is that? Plutoconium is like 233. And then it comes down to uranium 233. So it's a long supply chain. But once you get that, and again, it does take time, because the first beta decay is very quickly, 22 minutes later, it decays into second one to uranium-233, that puppy takes 27 days. So you have to keep swapping rods. Again, it will be it's a known problem. How to solve this is done. But we can have a scenario where reactor is there and you keep, okay, one feedstock, second feedstock, and then again, you cycle it back next year. So once we have the small amount of U233 to kickstart this puppy, problem solved. We will have a reactor that can directly digest thorium. That's the whole point. The aim is to have a reactor that creates its own uranium-233. Now you may be like, okay, you have a reactor technology. Why create this second stage? Why not just buy 233? Yeah, 233 is a kaboom material. It's not boom material, it's kaboom material. No country likes to sell it. Nobody wants to sell it. We do not want this to be on market. That's how bad this puppy is. So it has to be controlled. And going through this route actually gives you another benefit. Only competent people can reach this nationwide. Like you can't just like, lol. This is hard. Like this is not that hard. Like 235, you can do that enrichment. The Iran one, like they have enriched apparently this puppy to 60%. Yeah, 10% is more than enough for a reactor. I have seen some people claiming that you could use as high as 90%, but those will be a weapons grade reactor that is only used for submarines, because you need to make it very small. So this is a bit more involved, so to say. And does this have to be made out of sodium? Yes and no. You can make it out of sodium because again, we still want that fast neutron, but 232 has such a high velocity neutron emission that we may not need it. Again, may not need it. That part is not sorted yet to make a 233 reactor. There is enough designs for it and some experiments also with it, but again, I do not know what Indian government will select. Maybe it might select both of them. It's like, hey, you try with sodium, you try with heavy water or light water, and then let's see what's what. So that's the whole point. Take a normal uranium ore, imported, cook it, get the basically depleted uranium and plutonium, cook it with thorium, get a decent amount of U-233. Now run a reactor on 233 that directly has the ability to digest thorium that India has. So this is the three-stage plan. And this gentleman figured this out in 1954. I do have to say, sometimes like some elder Indians were like, damn, like they're good, like planned out so far ahead. It's like, damn. Oh, and it also gives us a freedom where we, like, you do not know how much nuclear boom power we have. Like, be good. If we cross all these three stages, like as much boom powder you want, we can make it. That's not an issue. And different varieties also, not just limited to, oh, this plutonium or this, like, we have so much flexibility. The whole bottom row of the periodic table is like, bro, it's open. So this is the three-stage plan. Step 1 we already did. Step 2 became critical now. Again, it was already finished last year, but it took all the nuclear reactors started very slowly. So now it's ready, it's going. I'm pretty sure in a few years from now we should have the U-233 reactor sorted. Either maybe a small prototype, or they might go for 100 kilowatt, 100 kilowatt, I'm saying 500 megawatt unit directly. I do not know, but that time will tell. And we should be able to shut down the phase 2 reactors, or maybe just run it as a experiment, because again, certain uniqueness does stay, specifically if you are using sodium. And this one, let's just say if it utilizes water, even light water, it does have some neutron moderation compared to that flat out full neutron flux. So that's the three-stage plan. So assuming you have not seen my year-old video, I'm repeating the same thing. If you have seen it, please skip it. So we are using liquid sodium as primary heat exchanger fluid. Be mindful, we cannot use water because we need neutron density, velocity, so to say. So we cook it here. Here's the reactor. Now reactor is cold generally compared to even a coal power plant. Coal power plants are bonkersly hot. The fire could start as 1000 degrees Celsius, and certain supercritical one can have fire as hot as 1600 degrees Celsius. So they're hot. This is not that hot. Like nuclear power plants are not, and that's why people keep talking about carbon dioxide turbines for this sort of thing, because again, it's not hot and you don't want it to be hot. So how do we boil water? Well, we put water there. Here's the problem. Water in that sort of radiation flux environment does not just have the risk of turning to steam, it has a risk of going kaboom because it will split into hydrogen and oxygen. So you have to pressurize the hell out of it. So pressure in this sort of system, basically you have the reactor vessel, and the liquid part, that is water, has to be so high pressure that it becomes very expensive. So if you use sodium, not only it gives you the neutron transparency you want, it also reduces the pressure. It's all running at 1 bar. Again, depending on the design, you can design it like 2 bar, 3 bar, but not bonkers. So it's super easy. So reactor heats up to, let's say, 547 degrees Celsius. It goes to a heat exchanger. That is like input temperature is 525 degrees Celsius. Output temperature is 355 degrees Celsius. Water goes into it. That is boils up to 490 degrees Celsius. Although I do not want the job of the inventor who has to come up with the heat exchanger. Yeah, sodium explodes when it comes to water. And you have ludicrously high temperature sodium, ludicrously high temperature water under pressure. So yeah, whoever designed that heat exchanger, that's the material engineering. So that's a difficult thing to crack. And then this drives into your turbine, high pressure turbine, low pressure turbine, medium pressure turbine, and that gives you the 500 megawatt electricity. Now be mindful, this electricity thing, that's just a side job. The reactor is not for this. It will help running cost and all that, but that's not the aim. Aim is this hot puppy. This hot puppy where you can basically create the uranium you need for the next stage. That's the all job it has to do. And again, how do you condense the water? Thankfully, this is next to the sea. They are using seawater. Like, wait a minute, wouldn't seawater cause salt deposition? Yes. So generally what they do is the condenser has a heat exchanger, and they make sure the water that is coming in never leaves at a boiling point. Meaning water comes in, let's say, This is seawater, let's say 28 degrees up to 30 degrees, let's say 35 degrees Celsius. You are absorbing 35 degrees Celsius, you'll make sure the hot only goes to 40, 45 degrees Celsius. Now, how can you throttle that? Flow rate. Flow rate is the vector that you control. So you make sure the boiling happens in the sea rather than in the condenser unit. You're not open pond boiling it. Another aspect, what about corrosion? That takes care of the bulk salt installation, but what about the corrosion? Generally, in this sort of environment, you have some sort of sacrificial metal that will be sacrificed to the gods of the sea, and then your material will be intact. Sydney Opera House also does the same thing. It's a sorted problem. I do not know exactly how they did it, but it's a sorted problem. And then the water repeats in the loop. And you do not want to change this water. This water, again, depending on how close this goes to the reactor, it will over time become radioactive. So I do not know how close this is, but if it's far enough and sodium is not coupling enough neutrons, it should be completely fine. But again, safety. And if you must have seen like some Chinese design of small modular reactor, they are using helium. That's the reason for it. You do not want water to go through the reactors. It becomes radioactive. Because again, neutron bombardment on hydrogen elevates hydrogen to one step up. Then it elevates it again, then it becomes radioactive. Then you die. So fundamentally, that's how we are making sure of it. And how do you safeguard this reactor? Here's the biggest problem with the nuclear reactor. They do not have an off switch. If you think there is a button that you press and reactor turns off, yeah, no, reactor explodes if that happens. And again, you need proof. Chernobyl also did that, and Fukushima also did that. Because again, there was an earthquake. Control system was like, hey, earthquake detected, serious earthquake detected, serious hazard detected, shut down the reactor. Everything worked as planned. Yeah, that was the problem. It shut down the reactor. Once it shut down the reactor, there was no power, no electricity. Cooling pump stopped working. This stove has infinite energy, practically speaking. Meaning you turn it off, all you are doing is, that's why you have to measure the megawatt thermal also. The megawatt thermal will go down, but it will not go to zero, meaning it will not return to ambient temperature. It has too much daughter products and so many things that are, going through its half-life change. It's hot, and I mean hot, meaning if you do not start to cool it, it will melt through the earth, that kind of hot. The elephant foot, that's the thing. So you must maintain cooling. And if you have seen the Chernobyl, why they needed to make sure that turbine can bridge the gap between power cut and backup generator turning on, that's the reason. The tub, the vessel must not lose cooling pressure under any and all circumstances. If it loses, even for a small duration, it can overheat bonkersly and tada. So, and that's what happened. But to be fair, that was only because of Japanese ego. More than enough people written letters, bro, all your backup generators are underground. You are next to the sea. Tsunami, the end. But they did not listen. Japanese ego, normal. So all the power plants, backup generators were flooded. You cut the power. There was no electricity. What can you do? In the end, you waited for pressure to blow up and kaboom. That was the first boom event. Oh, and now you know why the spent fuel needs a swimming pool that remains cooled for 2 years. There is no off switch in a nuclear reactor. So how do Indian people solve it? Well, we are like, hey, what's the benefit of sodium? Sodium's hot. What's the benefit of the reactor that is not that hot? As in, sodium can, let's just say, go up to 800 degrees Celsius. This puppy is only designed for 547 degrees Celsius. You can create a passive loop. Let that be repeat. Passive loop is just a pipe that has sodium. Over time, on its own, it will create a convection current, meaning hot sodium will rise, cold sodium will start to come down. There is a radiator on top. It will start to dissipate heat passively. No electricity needed. And we have 4 of these puppy. Each of these puppy can, cool down 8 megawatt thermal 24/7 without electricity. 1 of that. 4 of that. And again, it's not main reactor output, but it is daughter product output. And this should allow enough cooling that the structure remains intact without human intervention, without electricity. So that's how we are keeping the reactor boom proof. Hopefully, knock on wood. I'm hoping for that. So that's how they're doing it. How the heck you make sure the reactor does not go kaboom because it does not have a moderator? Well, sodium does come with one advantage. It has void coefficient, meaning once it heats up, expands, the neutron becomes too fast. Like again, ask a nuclear physicist how the heck that happens. But apparently, if it dilutes, basically the psi, basically if it heats up too much, the reactivity goes down drastically, meaning it will start to oscillate on its own. It will start to regulate on its own. And this backup systems we have should able to keep everything under check, even if let's say SCADA system poops the bed for a few minutes. So negative coefficient should give us the ability. And again, electricity is not the point. Point is taking fertile material of thorium and getting fuel out of it. So that's the design. Now, what is the goal? Again, this project is expensive and ancient. Like this project is older than I am. So to gain complete nuclear sovereignty, we should not pick up a phone. It's like, my man Putin, give us some stuff, or Kazakhstan, my man, give us something, or France, nothing, nada. It should not, like, we should like, bro, we good. Another aspect is not importing uranium ore. That's really good money saving. Another aspect is competency in fast neutron reactor. It's a whole separate field. Only few people on the planet has that skill. Not like, we have universities full of it. No, only few people. Because again, that's how rare that tech is. So having competency in fast neutron reactor, that's a whole, what you call tech tree opens up to you, where you're like, hey, what if I take carbon and make it into something else? What if I take basic carbon, make it into battery carbon, where it's like beta decay battery or something like that? You can make it. Like, there's a lot of options with nickel and all that. So many options open up if you have expertise in fast neutron reactors. So that's a good thing. Another aspect is nuclear transmutation is the whole study field that opens up when you have the reactor in-house. And enough U-233, this is the key part, enough U-233 to start the chain reaction. We do not need continuous supply. Even though it's a breeder reactor, it in principle can keep producing it, but that's not the aim. Aim is just to give enough, maybe 1 kilo, maybe 1 ton, enough to start next generation of reactor. So once we have that reactor, we'll have competency in U-233 thorium breeder reactors. That's the final stage. Once we have thorium breeder reactor, basically we dump thorium, it gives us U-233. We can decide either it remains in the reactor, being consumed over time, or we can give it to some other reactor to start that reactor, so we can keep amplifying it. So that, if done correctly, India will have complete supply chain. As you can see, the next closest puppy that has enough thorium is Brazil or Australia, or like you can say USA has 9%, Egypt has 0. Like we good, we more than enough. And you can see uranium, we have like some small concentration, and mining operation is just for safety sake. Safety as in like, you do want your national to have some uranium reserve. And thorium is like, bro, we good. We're like, we good, more than enough, we good. So that's the end point. End point, this belt should become the backbone where it's like, we have more than enough. Like, we do not have to ask, pick up a phone call, nothing. And whole supply chain and whole competency, we should be able to do it. This is Narendra Modi, and this is our reactor. Now, we come to the wisdom part. Nuclear sovereignty for a country that is this big, as in 1.5 billion, that is good. That is good. And Navy needs it. India has massive sea borders. Our patrol boats just, if they run on fuel, they can't do much. And we have two naughty nations. We have Pakistan going boom boom, and we have China going boom boom. It's not a safe environment, and we need to have enough oomph in our Navy to handle situations. So Navy needs it ASAP. Oh, and thankfully, that uranium allows you to make very tiny reactor. Basically, heavy water reactors are super huge, but the enriched one, they can be very tiny. We can like, bro, we good. I think this would be a bit too small, but the big one, we're like, bro, we good. And we have like, nuclear powered icebreakers, something like that. So having India's aircraft carrier, nuclear submarine, we do have nuclear submarine that is nuclear powered. But again, we do not have enough of it. We do not have hundreds of it. So, and again, I don't think we need hundreds of submarine, but having that would be not bad. And boats, really not bad. That would be a good thing. So that's the whole point. And nuclear competency is an advantage. A country that knows nuclear physics from start to finish, that's something. That's not something that's like any Tom, Dick and Harry can do. But be mindful, world has changed. While this was mind-bogglingly awesome in 1950, and even if we have achieved this puppy by, let's just say, 1990 and 2000s, it would have changed the country. But now it's too late. Why? Well, alternative power sources are too cheap. That reactor that is active right now, if it does not make enough power to justify its cost, which it cannot, it physically cannot, it is too over budget, too delayed. So money wise, it will never ever break even. That's okay. We are not making it to get power. Power is just like, running cost maintenance. But that will not be the end game for all the reactors. Like that's cool, okay, for some nuclear reactor research, physics and all that. That's like a country's investment for long-term prosperity. That makes sense. But nuclear power plant, yeah, there is a very specific reason in this whole presentation. I did not talk about the presentation or the delay. So that's the whole thing. Fundamentally, the price of alternative sources have dropped drastically. And world is not stable enough pace for nuclear for long term. Like war is yesterday. Terrorism is Wednesday. This is normal scenario, and having lot of nuclear power plant, it's a target rich environment. Now Americans think that nothing bad will happen. Again, they have the luxury that there's not really that much threat nearby, but other countries, again, Pakistan is nearby, China is nearby. We have to design for that, and if we put too many nuclear power plant, that becomes a hassle for us, that Air Force now have to defend it. So again, that's happening in Russia-Ukraine one, in Chernobyl right now. It's not like if this then that, it happens. So it's not a safe idea to have too many nuclear power. Some good, cool, awesome. But it should not be like, yeah, and it will never be cheap to be cost effective anyway, unless you subsidize the hell out of it. Why is that? Well, see, how many people do you think knows how nuclear transmutation works? Like how many people can inherently watch Chernobyl and say, what the hell do you mean xenon poisoning? Where the heck xenon came from? Like that's not a common thing. And having enough competency, not only knowing, enough competency that under pressure you do not kaboom the reactor, that's a very short list. And you have to train them and you have to pay them. And if you have to pay them a lot, how the heck are you going to make the money back? Because again, that was not an issue when your competition was only only coal and only natural gas. But that era has gone long by. We have hydro, very powerful hydro. We have bonkers solar, super cheap solar, and wind. So the world has changed, let that be clear. And from a strategic point of view, humanity cannot handle a planet with carbon dioxide poisoning. It will not be able to handle nuclear waste proliferation. Like we will not. Okay, this whole idea is like, but what if we drill it? It's like, who is paying for that? Everything is subsidized. That subsidy simply means it's from your pocket. So why create that mess? Again, from a development point of view, from a weapons point of view, go GG, but not as a power plant. And you must have seen basically boom places like Iran and Gaza, which houses had electricity afterwards? Only the houses that had solar panel. That's the whole point. Distributed energy is the future. You want energy to be distributed. Some nuclear power plants, cool, awesome. Like somebody was fighting with me. It's like, oh, France has so much nuclear. Yeah, it's nothing. It's less than, like France has so much nuclear power. That's the main mix of their nuclear power. Yeah, it's 1/3 of India's total energy requirement. And India is growing. And I'm not even going to dare to compare it to China because that's 10x smaller. We need cheap and abundant power. Solar meets that battle, not nuclear. The world has changed. And again, mix it with wind, mix it with pumped hydro, which again evolved because of nuclear. And again, there are other designs also, because the power cost is so low that if you come up with a plant, it's like, I want to convert a coal power plant into a battery. And it's like, it's very wasteful. People can still do it. We are still doing it. It's in Asansol, in India, West Bengal. Why? Because that's the whole point of solar. It's so cheap. You can store it. You can add grid inertia to it. All the problems that it has can be solved. And two scales, one massive scales and rooftop scale. And that gives country resilience. So again, we have to apply wisdom. I want nuclear submarines. I want nuclear boats for our sailors. But I don't want nuclear everywhere surrounded with our civilian infrastructure. That's a boom target. That's like painting a bullseye target. So fundamentally, that's why I did not talk about the delay and the time frame. To give you a context, the amount of money we spent, we would have made solar farm in India, got electricity out of it, did the ROI, then doing the profit, and it still would be in delay. That's how, like, delta between the reality delivery of nuclear versus what we have with solar, what we have with wind, what we have with hydro, what we have with everything else. And I'm not even touching biogas, which we have to solve, otherwise we will cook ourselves. Yeah, like, world has changed. That's why, like, I do not get this idea, like, nuclear. It's like, I get it, you may think like human can handle nukes, but nuclear technology does not tolerate oops. And human always does oops. So that's the wisdom part. If we are wise about it, we might be fine. If we are not, inflation will go stupid high. So this was my presentation on basically what is India trying to do and the big step that we have made. We have cleared the second stage now. Now the generation of next feedstock for third stage is beginning. So I hope you have liked the presentation. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.